In this video, we're going to be talking about geometric sequences, a second special type of sequence. So just to kind of recap, in this unit we talked in general about patterns and notation. Then we talked about arithmetic sequences where we were always adding by a common difference to get the next term. And now we have a type known as geometric sequences where we're always multiplying by something to get the next term. That something we call the common ratio, and we use the letter R to denote it. What's the common ratio for this first purple sequence? We can see that we are always multiplying by 2 to get from one term to the next. 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24, 24 times 2 is 48. So our common ratio, R, in this case, is going to be 2. Let's think about how we would try to write a rule for this geometric sequence. Our first term is 3. Our next term is 6, but I'm going to write that as 3 times 2. Our next term is 12, but I'm going to write that as 3 times 2 times 2. 24, you guessed it, 3 times 2 times 2 times 2, and so on. I think you see the pattern. How many times are we multiplying each term by 2? Well, this is 3 times 2 to the 0th power, because we're not multiplying by any 2's at all. 3 times 2 is, of course, 3 times 2 to the 1st. Here we have 3 times 2 squared, 3 times 2 cubed, etc. So how could we get the nth term? Well, our first term had an exponent of 0 on the 2. Our second term had an exponent of 1. Our third term had an exponent of 2. Our fourth term had an exponent of 3, etc. So our nth term is going to look like 3 times 2 to the n minus 1. Notice that exponent on our common ratio is always 1 less than the term number. So our explicit rule, an, is equal to 3 times 2 to the n minus 1. Notice order of operations would state that I have to do the exponent first, so that is not the same as 6 to the n minus 1. It is 3 times 2 to the n minus 1. The recursive rule is probably a little bit easier to see. To get an, I would take 2 times our previous term, an minus 1. And of course, for our recursive rule, we also have to state that our first term is 3. Let's state this in general. In general, if we have a geometric sequence with common ratio r, our explicit rule is going to be our first term times our common ratio to the n minus first power. Hopefully you saw that from the pattern on the previous slide. We're always just starting with our first term and then multiplying by r some number of times. That number of times is 1 less than the term number we want. Our recursive rule is going to look similar to what we saw before. Take your common ratio and multiply it by the previous term. That will give you the next term. And of course we have to say whatever a1 is equal to. So we put that there as a reminder. Now we have a general form for an explicit and recursive rule for any geometric sequence. Let's try this example. Here we have a sequence 52, 26, 13, 13 halves, etc. What are we always multiplying by? The first thing you might notice is that we're always dividing by 2. Well, remember, division is the same as multiplication by the reciprocal. I always want to think about multiplying by a common ratio for a geometric sequence. So when I hear division by 2, I think multiplication by 1/2. So in this case, our common ratio is 1/2. So notice our directions. We need to write an explicit and a recursive rule, and then we have to find a10. We have to find the 10th term. Let's get the recursive rule first. Well, I know that I'm taking, to get the nth term, we take the previous term and multiply by 1/2. Of course, that 1/2 could go out front. Multiplication you can write in either order. And then I also have to say that a1 is equal to 52. Let's try to find an explicit rule. using what we saw on the previous slide in general, I know that to get our nth term, we would take our first term, which is 52, and raise that to the common ratio, times the common ratio raised to the n minus first power. 52 times 1/2 to the n minus 1. Notice how important the parentheses around our common ratio is here. If we didn't have the parentheses, then it would look like 1 to the n minus 1 all over 2. But we're raising that whole fraction 1/2 to the n minus 1. So we really need parentheses for this common ratio. And our last question, find A10. I'm going to use the explicit rule for that because I don't feel like finding A1 through A9 first. So let's use our explicit rule. A10 is equal to 52 times 1/2 to the 10 minus 1. If I simplify that, that's 52 times 1/2 to the 9th. Now think about what it means to raise 1/2 to the 9th power. That's 1/2 times 1/2 times 1/2, etc. 9 times, or it's 1 over 2 to the 9th. And we get 1/512th. So our 10th term is 52 over 512. If you want to reduce that, I think that reduces to 13/128ths. That should make sense that our denominator is 128. That's a power of 2, because you were always multiplying by 2, multiplying by a half, multiplying by a half, multiplying by a half. So that should make sense. All we did there was plug in 10 and simplify. Let's go backwards. This is telling us that a term in the following sequence has a value of 295,245. What term number has this value? Let's first see if we can get an explicit rule and then maybe do some plugging in. Let's see, 5, 15, 45. It looks like each time we are multiplying by 3. Now I know we can get our explicit rule. Our nth term is our first term times our common ratio to the n minus 1. Now let's think about what we'd have to do. We need to know what term number has that value. So we're going to plug in 295,245 in for an. And let's see what our equation looks like. This is an exponential equation. Let's try to get our exponential piece by itself first. We can do that by dividing both sides by 5. And we get 3 to the n minus 1 equals to 295,245 divided by 5, which is 59,049. Hopefully you're following along with me on your calculator. How do we solve this equation? 3 to the what equals 59,049? We kind of have two options today. Option number 1 is use logs. Logarithms. Of course we all remember those. And if we don't remember those, that's not good because they're going to be on our final exam. So this might be a great time to review. I know that we can take log of each side, or I can think about putting this exponential equation into log form. Log base 3 of 59,049 is equal to n minus 1. In order to figure out what log base 3 of 59,049 is, you can use the change of base formula. Log of 59,049 over log 3. So I'm using two logs both in base 10 in order to plug that into my calculator and figure out what it is. Turns out that when you plug that in, log of 59,049 divided by log 3 is 10. Careful though, 10 is not our answer. 10 is equal to n minus 1. So we have to add 1 to both sides to get that n is equal to 11. Our 11th term in this sequence is 295,245. So our 11th term is really our answer. Let's say I don't remember logs at all. Let's talk about another way to solve that equation. Remember, we're talking about 3 to the n minus 1 is equal to 59,049. How could we do this without using logs? Well, think about what type of number n has to be. N is a counting number. It's a term number. It's not going to come out to be something like 2.718 or negative 3.2. It's going to be a natural number. Because it's a natural number, it's not that terrible of an idea to use guess and check. And even though you might think 59,049 is a large number, in terms of powers of 3, it's not crazy large. Like, it's not going to end up being 3 to the 100th or something like that. So if you're not sure what to pick to guess and check with first, pick any power of 3. How about if I just pick 3 to the 5th? And if I try 3 to the 5th, I get 243. Okay, that's not big enough. How about 3 to the 8th? Remember, we're trying to get 59,049. 6,561 is 3 to the 8th, still not big enough. Maybe I'll now guess 3 to the 10th. I don't know, just jumping up a little bit. Oh, and I get 59,049, so that's what we wanted. But remember, n is not 10. N minus 1 was 10. So we still have to do that very, very last step of adding 1 to each side and get 11. So if we're working backwards with geometric sequences, I recommend you use logs. It's definitely faster. But think about the type of number that n is. Because it's a natural number, it's really not that crazy of an idea to use guess and check. And I think it's a nice way of bringing back that idea of estimation. Can you estimate roughly what the exponent will be to use some good guesses? Good luck!